Welcome you all in my next lecture. So, in this lecture I will talk about of course, I discussed about mixed derivatives theorem, mean value theorem, Bayesian. So, now only part is remaining is to talk about Taylor's theorem, right. Taylor's theorem you are familiar with in single variable calculus, right. If I have a function from say R to R or say some closed interval a b to R, then you know the statement of Taylor's theorem. And in my last lecture I talked about like some importance of Taylor's theorem. So, I will start with that. I will introduce the notion of Taylor's theorem in the context of multivariable functions, and let us see how it works in this setting as well. Okay. So, now just look the statement. I think this slide is for extended mean value theorem. Now, Taylor's theorem you know that like for example, single variable calculus like I already discussed the importance of this theorem. So, now Taylor's theorem like you can also think about is an extended mean value theorem. If you just look at the statement what I have written, that let f be a functions from some open set S subset of R into R real valued functions or scalar field I should say, and if I have a point capital A which is in S, and if I say take the point capital H which is small h1 up to small h n in Rn be such that what I want is that if I have a set S and I am fixing a point A, and then I want that the point A, and of course I am taking another point H, in fact I am perturbing my point capital A. So, capital A is a fixed point, I am perturbing with capital H. So, I have a point A and A plus H. So, that means I have 2 points inside my set domain S, and I want in such a way so that the line segment joining these 2 points should also in that set. Okay. If that is the case, and suppose if the DIF means I have the existence of first order partial derivative with respect to xi variables I running from 1 up to n. If this exists and continuous, then of course I can talk about the another assumption is that, so what I want that first order partial derivative should exist and continuous. Along with that Dij, that means it is the second order partial derivatives, that should also exist not only at the point A and A plus H, but also at the points in the line segment L joining the points A and A plus L. Okay. Then if this is my hypothesis, then it says that then there exists a point P A plus theta H. Now, A is a given point, H I am perturbing it, and I am considering the point A plus theta H, theta running from 0 to 1. So, that means I am having a point A plus theta H in the line segment capital L. If this is true, it says that then there exists a point P on the line segment L joining the point A and A plus H such that you will have the expansion of the functions near about the point A. F of A plus H is exactly equal to F of A. Then you will have H1 D1 dot dot up to Hn Dn. What is D1? D1 is partial derivative with respect to x1 variable del x1. So, that means D1 is nothing but del x1 up to Dn means del xn. And then I have a bracket acting on f restricted to a. That means you just calculate the first order partial derivative of f with respect to x1 variable, x2 variable up to xn variable, okay, at the point A, and then hitting with by h1. So, that is the meaning. And then what we will have? You will have another term that contains the second order partial derivatives. Now, if you remember when I was talking about in my last lecture the existence of mean value theorem, what is that? That means if I have a function, nice function say from an open set, suppose S is open and convex, then if I take any 2 points A and B such that the line segment, of course convex means that if I take any 2 point A B in S, that means the line segment already inside that one, then if you look at the statement, it is like f of B minus f of A, which is exactly equal to derivative of f at some point xi or some c times B minus A. So, that means if I change B by A plus H, so that means if I consider, so if I go back the earlier one, then it will be more clear. What I am trying to say is that if you replace this is by A plus capital A plus H and this is capital A. Okay. So, then what will have? F of A plus H minus f A, then what will happen? This is the gradient of f at c, that means containing the first order partial derivative of f with respect to some x1, x2, xn at the point c dot product with b minus a, that means it contains the terms consisting of first order partial derivative. That means what is your b minus a? In that case my b minus will be h. So, what will happen? This is actually if I consider, so this is del f del x1 at c up to del f del xn at c dot product with h. H means if I write h1 h2 hn then what is this? This is H1 del f x1 at C up to Hn del f del xn at the point C. You see, so that means f of a plus h minus f a, which is nothing but the combinations of h1 h2 hn with partial derivative of f with respect to xi variable at C. So, that means h1 times del f del x1 at C plus h2 times del f del x2 at C up to hn times del f del xn at the point C. So, that means this is kind of mean value theorem, you know. I am saying that Taylor's theorem, at least for the second order, is nothing but the extended mean value theorem. That is what I have written this word, that it is extended mean value theorem. So, that means if you look at the expression, it is f of a plus h is equal to f of a plus, this is the first order term, that if I talk about mean value theorem, it appears. Now, I have an extra term that consisting of the second order partial derivatives. And when I will talk about Taylor's theorem, sometimes I will see if I talk about the Taylor's theorem say order n, then there will be a remainder term consisting of n plus 1 mixed derivative of f. So, that is why this is sometimes called extended mean value theorem or Taylor's theorem of order 1, I should say. Okay. So, but as I said that Taylor's theorem in single variable calculus has a very important kind of consequences in many things, like for example, I said that what is the importance of Taylor's theorem. So, if I want, suppose I have a complicated functions f and I would like to investigate the behavior of my functions around the point A. Okay. So, Taylor's theorem says that yes, if I have a functions, complicated functions say f and I would like to investigate the behavior of f around that point A. So, Taylor's theorem implies that okay, you can approximate your functions near about that point by some polynomial. Okay. So, that I will explain once again explicitly what do I mean by that. So, that means I can approximate my functions in a neighborhood of A with some polynomial, and polynomial are well behaved. So, Taylor's theorem says a very important fact, that means I know the behavior of my functions around the point A, that is very important. And like as I said in my last lecture, that suppose you have a mathematical problem and you do not have the analytical solution. Okay. But using Taylor's theorem, since I have no idea about the analytical solution, I can give some approximation solutions and that actually possible via Taylor's theorem. You could have a solutions of some mathematical problem, approximating solution, that you can do that. And actually these kind of things are very much useful in like say differential equations or say numerical analysis, and I think recently machine learning and everywhere I think the applications of Taylor's theorem is useful. So, in a single sentence I should say that in single variable calculus, that means if I have functions from R to R, I can approximate my functions near about a point say fixed point say x naught by some polynomial, or in other words I should say that if I know the value of my functions at that point along with some derivatives of some finite order at that point, if I know the value of the functions at that point along with some derivatives at that point, then I can construct a polynomial and then I can approximate my functions near about that point with that polynomial. So, that is how I somehow I know the behavior of my functions. So, similarly one can ask, okay, if I have a functions from say R2 to R or say Rn to R, now can I have a, suppose I have a complicated functions and can I have a Taylor's theorem, or can I say that I can approximate my functions near about that point with say polynomial of 2 variables or say polynomial of n variables if I work in Rn. So, similar sort of theorems you can also ask in the context of several variable calculus, and answer is yes, since I have the notions of say like partial derivative, directional derivative and total derivative. So, there are also a kind of appropriate extension of Taylor's theorem in the context of several variable functions, and there also I can conclude that yes, if I have a functions f which satisfies certain properties, then I can approximate my functions near about that point via polynomials, and in fact I know that I can talk about the behavior of my functions. So, that kind of things you also see in the context of multivariable. So, this is extended mean value theorem or Taylor's theorems of order say 1. So, now if I want to state the exact Taylor's theorem for functions f from Rn to R. So, this is the kind of corresponding statement. This is I have written the Taylor's theorem. Now, what is the statement? Statement again. So, I think I should again, so this is actually I should talk about little bit. So, for n is equal to 2, what I have done, I just expand this object and this object, you see. Now, if n is equal to 2, that means I will have only first order partial derivative, then del f del x and del f del y, and then I have h1 second order partial derivative. How many partial derivatives will offer? 4 partial derivatives, that means del 2f del x square, del 2f del y square, del 2f del x del y and del 2f del y del x. Okay. So, I have just expand for n is equal to 2. So, f of a plus h, which is exactly equal to f a. Now, what is this? So, this one will give you this object. h1 partial derivative of f with respect to x variable or x1 variable at the point a, and then h2 times partial derivative of f with respect to x2 variable at the point a. This is containing the first order partial derivatives. Now, it comes, so this one is coming from this one actually. That means, it is about the second order partial derivatives. So, now how many second order partial derivatives we will have in the context of n is equal to 2? I will have 4 second order partial derivatives. What are they? So, they actually del 2f del x square, del 2f del y square, then del 2f del x del y and del 2f del y del x, right. But as I said, that second order partial derivatives, suppose if I assume nice condition that second order partial derivatives exist and continuous, then del 2f del x del xy is exactly equal to del 2f del y del x at that point. So, I have written here actually, you see, this is containing del 2f del x1 x square or x1 square, whatever it is, and this is actually d22, that means del 2f del y square or del 2f del x2 square. This two part is perfectly all right, but what will happen, this one, this is the mixed one actually, mixed partial derivatives. So, that means I have to first take the partial derivative with respect to x and then y, or with respect to y then x, but I have actually combined it. So, I am writing 2 times h1 h2 both are same. So, that means I have assumed that means the mixed order partial derivative exist and they are equal. In fact, you know that if their mixed order partial derivative exist and continuous, then automatically they are equal, and therefore, this is automatically true. So, that means while I am writing this one, so I assume that mixed order partial derivative exist and they are equal. In fact, it actually reflects in the statement of the following general statement of the Taylor's theorem. Look, so that is what I am trying to say. So, let f be a map from say some open set S subset of R into R. Okay. So, fix a point capital A in S. So, again take a point capital H in Rn. So, I am just perturbing my point capital A by H, be such that in such a way, so that the line segment L joining A and A plus H lies inside S. In particular, if I start with S is a convex set, then it is okay as long as A and A plus H is inside that set S. And what are the assumptions I am taking? You see, suppose that f and its partial derivatives through order m plus 1. So, now if I want to talk about Taylor's theorem of order say m, so that means I want that the partial derivative of order m plus 1 exist and is continuous. Now, when I am talking about the continuity, that means while I am talking about the mixed partial derivatives, then their value should be equal because of this continuity. So, that is why earlier I think I have assumed that one, or that this mixed partial derivative exists and they are equal. So, therefore, value will be same mixed partial derivative. So, what is this? So, this is my assumption. Suppose f and its partial derivatives through order m plus 1, because I want to talk about Taylor's theorems of order m. In fact, this is called the remainder term. Okay. So, then what will happen? Then there exists a point P, which is a plus theta h, where theta running from 0 to 1, such that this is the expansion of my functions f near about the point A. So, what is that? This is like in the single variable calculus, but in the single variable calculus in the Taylor's theorem, it contains only the derivative of f. Here I am, since I am dealing with the functions from Rn to R, then it should deal with the partial derivatives, second order partial derivative, mixed partial derivatives. It depends upon what order I am talking about. Since I want that Taylor's theorem this, then f of a plus h is exactly equal to f a. Then you will have k from 1 up to m, 1 by factorial k h1 d1 dot dot hn dn to the power k. So, I will explain what is the meaning of to the power k. To the power k means is just nothing but the binomial expansion. You have to consider the binomial expansion. This is the notation. Acting on f, you have to perform at a, and then you will have the remainder term. So, this is the appropriate statement of Taylor's theorem in the context of several variables. I should write that. What is this? So, this is I think h1 d1 means del x1 up to hn del xn to the power k. That means you have to somehow perform the binomial expansion, and then calculate the partial derivative of f at the point A, and that is corresponding the notation, and this is called the your what is called remainder term. So, that means I know the expansions of my functions f around the point A. So, this is the expansions, and finally, you have a remainder term which is of this kind of form 1 by m plus 1 factorial h1 d1 up to hn dn to the power m plus 1 of f acting on p. That means this is the binomial expansion you have to consider. Then you have to have a kind of differential operator there, and you have to like do the partial derivatives of f with respect to that order, and at the point p you have to evaluate. So, that is the kind of expansions of f near about the point with this is the remainder term. Now, if I take n is equal to 2, then I will explain what is the exact meaning of this and this. I think that I have explained. Yes, look. So, Taylor's theorem for the case n is equal to 2. What is this? So, now consider, just focus that I have a functions from R2 to R, okay, n is equal to 2. Then what are the, suppose if I want to talk about Taylor's theorem of order m. So, suppose this is my, see, as I said, so this actually earlier you will have what, h1 d1 plus h2 d2. So, now I am just writing h d1 plus k d2, or I think I am writing h del x, because in this case I am actually functions of two variables R2 to R, h del x plus k del y. So, this is my operator, and I am writing as f prime. Okay. So, now if I have a function, let f from R2 to R, set the differential operator capital F prime, which is nothing but h del x plus k del y. Then when I will talk about f double prime, that means I am talking about the square of that, and what is that square? It is just the binomial expansion. So, that means h square del 2 del x square plus 2 h k, again you see I am just combining two mixed partial derivatives, because I assume that continuity. Earlier I have assumed this continuity of m plus 1. If I want to talk about Taylor's theorem of order m, then m plus 1 order exists and they are continuous, therefore mixed order partial derivatives should equal. Okay. So, therefore, this is okay, and then I have k square del 2 del y square. Okay. And similarly, if I have f prime, f double prime, f triple prime, similarly I can talk about f m bracket m. So, this is again, this is h del x plus k del y to the power m, and you have to expand it by binomial theorem. So, that is the meaning of these notations. Okay. Okay, so that is about the kind of version of Taylor's theorem. If I have a functions from some set S subset of Rn to R, and suppose this function is, or suppose your set S is a very nice open and convex set, then if I take 2 points, if I fix a point capital A, then if I perturb it by H, capital H, and such that A and A plus H lies inside S along with the line segment joining A and A plus H, and if I assume that my functions and its partial derivatives through order m plus 1 are continuous in S, then there exists a point in the line segment L P, that is A plus theta H, such that this is true. Okay. So, that means that I will explain in my next slide. That means, in other words, I can approximate my functions f near about a point A via polynomials. In this case Rn, that means I have a polynomial of n variables. When I will talk about R2, that means I have a polynomial of 2 variables, and if I have a functions of real valued functions of real variable, and that you know that I can approximate my functions near about a point A via polynomial just single variables. Okay, this is the Taylor's formula. This is now I have a n is equal to 2, I have a functions from some nice set A subset of R2 to R, and then I want to talk about Taylor's theorem and along the remainder term. So, this is called Taylor's formula I have written. So, suppose f of x y and its partial derivatives through order n plus 1 are continuous throughout an open rectangle R centered at AB. So, that means I have, this is my R2. So, I have something say in this square I want to talk about. So, suppose this is my point AB. So, I have a nice neighborhood around the point AB. I am saying that the rectangular region R, this is I am talking about, this is R. Okay. Then throughout R I will have these expressions of my functions f near about the point A. So, what is the statement? So, f of A plus H comma B plus K is exactly equal to f of A plus B. Then you will have a expression in terms of nth derivatives like R from 1 up to n 1 by factorial R H del x plus K del y to the power R, and that you know I have a binomial expansion, plus you will have the remainder term. And what is the remainder term? This is exactly equal to 1 by n plus 1 factorial H del x plus K del y to the power n plus 1. You have to do the again binomial expansion. You have to perform the partial derivative of f, and then you have to talk about the partial derivative at the point a plus ch comma b plus ck, okay, where a plus ch and b plus ck, where for some c, or actually in my last slides I talked about theta, so the theta is replaced by c, is a point in the line segment joining a b and a plus h b plus k. So, this is actually the Taylor's formula in or for the functions f from R to 2R, because if I have a functions from R to 2R, then I will have only first order partial derivative is del x del y, and accordingly second order partial derivatives or third order partial derivative will be there, and the corresponding expression of the Taylor's theorem is this one. So, now I will explain. So, Taylor's formula for f gives a polynomial approximations, how it is that. So, you just think about your single variable calculus, then you will be able to see that how I am saying that Taylor's formula of f gives a polynomial approximation. For example, think about your functions f, say if I have a functions from say f from say closed interval a b to r, okay. And suppose I want to talk about the Taylor's theorem around the point a. So, therefore, you have an expansion. So, what is that? So, this should be f of say x naught plus h is equal to f of x naught plus h into a prime x naught, okay, up to, so h, and then I think right h then h square by factorial to f double prime x naught up to h n to the power factorial n f n x naught, and then you will have a remainder term. So, that means h to the power n plus 1 divided by n plus 1 factorial f n plus 1, and then you will have a x naught plus theta h. So, that was the statement Taylor's theorem, you know. Now, what I am trying to say is that this one you can say that I can write f of x naught plus h minus p of h, and what is this is same as I am writing h to the n plus 1 divided by n plus 1 factorial f n plus 1 and then x naught plus theta h, okay. And what is my pH? pH I am talking about this. This is f of x naught plus h into f prime x naught up to h to the power n by factorial f then f n x naught. Now, look, so what is given? So, I have a given that value of the functions at the point x naught along with couple of derivatives evaluated at that point. Now, these are the point or value you know. So, that means it is a function of h, in fact, it is a polynomial in h. So, that means what I am doing is that I am just taking point of fixed x naught, I am just perturbing by h. So, that means I am looking at a neighborhood of the point x naught, and the functional value minus this polynomial, this is actually this is called the remainder term. So, therefore, if I take the absolute and if I somehow get some kind of estimation, so that means I am approximating my f via polynomial using that expression of Taylor's theorem. That is what exactly going on in the case of single variable. Now, here look, so if I want to talk about n is equal to 1, that means let us say first order Taylor's theorem, that means what will happen? Then you will have f of x naught plus h is equal to f of x naught plus h into f prime x naught plus you have a remainder term something. So, that means it should be h square by factorial 2 times f double derivative at the point x naught plus theta h. So, that means look what I am doing is that, so this is remainder term. So, that means what it implies that f of x naught plus h minus some polynomial ph, okay, and this is the approximation is nothing but this is the remainder term. Now, what is p of h? In this case your p of h, if I write it here, so your p of h is exactly equal to f of x naught plus h times f prime x naught. That means it is a polynomial, that means it is a linear polynomial, or as we said that it is a linear approximation. That is exactly going on for n is equal to 1. That is what I have written. Of course, this is actually I am talking about functions of several variables, but let me understand in the function of single variable what is going on. So, single variable, that is why exactly the same thing. If I want to talk about Taylor's theorems of order 1, that means it is actually I am approximating my value, I am approximating my functions near about a point x naught via linear polynomial. And when I will talk about n is equal to 2, then again you see what will happen, again h square by factorial 2, that means another factor of h square will come, that will give you quadratic approximation, and n is equal to 3 it will give you cubic approximation. That is what is going on. So, now this is for single variable. Now, what will happen for the multivariable case? Exactly the same thing, because look at the expression you have already done. So, look, this is the expression. So, like, so if I write it, so that means, so I want to talk about linear approximation. So, what I have done for n is equal to 1, so f of a plus h comma b plus k, okay. What is this? This is f of a b plus h into, look, earlier one, f of ab h del x plus k del y. So, that means h into del f del x at the point ab plus k into del f del y at the point ab, plus you will have a remainder term, because I am talking about n is equal to 1, and what is my remainder term? This is my remainder term. So, that means it should be what? It should be 1 by factorial 2, then you will have h, what will happen? Yeah, del x plus k del y f at the point a plus theta 1 h, I think I have written what? A plus ch plus b plus ck. So, a plus ch comma b plus ck. So, this is my remainder term, say let it be r. Okay. So, now you bring back this one. So, what will happen? So, that means you are actually f of a plus h comma b plus k minus f of ab minus this del f del x comma ab plus k del f del y at the point ab. Okay. So, this is whole thing is exactly equal to your remainder term. But what is this? This object f of ab minus this is what I can write is polynomial of h and k. Okay? So, that means I am approximating f of the value of functions near about a point ab by a polynomial in hk, and this polynomial is what? Linear polynomial, because you have only combinations of h and k and some constant term, and this is the remainder term. So, if I estimate my remainder term, that means I am approximating by I am looking at the I can talk about the behavior of my functions using the Taylor's formula, Taylor's theorem near about a point ab. Okay, and that polynomial is nothing but a linear polynomial, because it is nothing but a functions of h and k. So, now if n is equal to 2, then what will happen? Then again the of course f of ab plus first order partial derivative will be there, and then what will happen? H del x plus k del y square will come, and that square will give you the polynomials of h and k, but this time it will be a polynomial because square term will be there. Of course, h and k term will be there because first order term will be there, first order partial derivative. So, that it will be a polynomial of degree 2. That means, I am talking about the quadratic approximation. For n is equal to 3, what will happen? I am talking about the cubic approximation. That means, the polynomial you will get, it will have a term like constant terms, term of h and k, term of h s k square, and then terms containing h q and k q. So, therefore, as n increases, then the corresponding degree of polynomial increases, and I am approximating my functions with respect to that polynomial of degree n. So, that is exactly going on. In fact, the similar phenomenon also happen in the real case, because in real case you will have only one variable, single variable, that when I can talk about the polynomial. But when I will talk about the functions of several variables, that means it is expected, that means if I want to approximate my complicated functions near about at that point, that means the polynomial, the variable, of course it should be there. Like if I want to talk about functions from R2 to R, that means the polynomial of two variables should come into the picture. Similarly, if I have a functions from Rn to R, that means polynomial of n variables should come into the picture, and answer is yes, this is the case. And in fact, the expressions of Taylor's theorem says is exactly like that. Okay. So, I can approximate my value of the functions, or I can approximate my functions near about that point by a polynomial of degree n, depending on which order I am talking about. This is just simple example I have given. So, like if in some problem, if I say that okay, calculate this is my functions, compute the first two terms in the Taylor's formula near about some fixed point. So, that is exactly you can do that, because once you know the formula, you have to just what you have to do, you have to just perform partial derivatives, and that is it at that point. So, look, this is my functions f of x y is equal to 1 by x times y if x y is non-zero. Okay, and take a point a b, which is a fixed point a 1 minus 1, that you can vary, not an issue. Then compute the first two terms in the Taylor's formula of f near about the point 1 comma minus 1. So, what you have to do, you know the formula, right? That means f of x plus h comma y plus k is equal to f of x y plus the first order partial derivatives, and second order partial derivative will be there. Okay, so it depends that how many terms I am telling you to compute. Okay, since I am saying the first two terms, of course, this function is nice. Of course, therefore, if x y is non-zero, that means very nice, all the first order partial derivative, second order partial derivative, these are exist. So, therefore, if you just calculate it, f of x at the point x y, the keeping f of x means what? That means you just keep y variable fixed, just take the derivative with respect to x variable. So, you will end up with minus x to the power minus 2 y to the power minus 1, f y you can easily calculate minus x to the power minus 1 times y to the minus 2. Again, you can calculate f x x, f x y, f y y. and f x y is it will be same because partial derivative exists and they are continuous because x y is non-zero. So, therefore, now you can have the expression in terms of Taylor's formula, Taylor's theorem. It says that 1 by f of what I am talking about 1 at the point 1 comma minus 1, that means f of 1 plus h comma minus 1. So, that means what you have to do 1 plus h then minus 1 plus k. So, what is this? This is nothing but this value, and then what is this? This is f of 1 comma minus 1, which is minus 1. That means then what will happen? You will have the first order partial derivatives, right. If I evaluated first order partial at the point 1 minus 1, this will give you the terms h minus k. So, that means what will have? So, if you remember, this is nothing but f of 1 plus h minus 1 plus k plus h into del f del x at the point 1 comma minus 1 plus k times del f del y at the point 1 comma minus 1, and del f del x you know and del f del y you know, just evaluate it at the point 1 comma minus 1. So, this will give you your h minus k, and similarly you can talk about your second order, because I am talking about first two terms. Okay, that means the first derivative and the second derivative you have to compute, and second derivative is also okay. So, that means del 2f del x square plus del 2f del y square at the point plus del 2f del y del x or del x del y, but this time functions mixed partial derivative they exist and continuous. So, therefore, it does not matter any one mixed partial derivative if you calculate it will be enough. So, that is what I have done it. Okay. So, again, so already f x x, f y y and f x y is there, you just have to evaluate it, nothing else. So, this is nothing but of course, at the point theta h, because the point if you remember the point, what point I am talking about 1 comma minus 1 plus some theta times h. H means h comma k, at that point you have to evaluate, and this is exactly give you this term. You have to just use the formula, that is it. So, this is the formula if you remember, yes. So, this is the one you have to calculate. Second term I am talking about, so that means this is the one you have to calculate at the point 1 comma minus 1 plus theta times h comma k, theta running between 0 to 1. If you calculate it, it is okay, because f x s is given, f x y is given, f y y is given. So, f x y at the point this what 1 plus theta h comma minus 1 plus theta k, that is what you have to use. Okay. So, what will happen f x x del 2f. So, that means this is the expression. So, that means it should be h square divided by this one. Yes, perfectly all right. I think, yeah, maybe 2 is missing, could be the case 2 is missing, I think, yeah, that I think it should contains 2, I think, yeah. Just check it, okay. No, I think 1 by n plus 1 factorial is there, 2 will get cancelled. 1 by n plus 1 factorial, 1 by factorial 2 will be there, and that 2, so 1 by 2 and this 2 will get cancelled. Another 2 will come in the, yeah, okay. So, that is perfectly all right. There is no calculation mistake, this is perfectly all right. So, what you have to do, so that means that is, you just calculated this one, na? So, that means 1 by factorial 2, then what will happen, del x plus del y to the power square of f at the point 1 plus theta h, then minus 1 plus theta k, right. That is what you have to do. And what is this 1 by 2, and then what will happen, acha, this should be h and this should be k. Okay, this should be h square del 2f del x2 at the point 1 plus theta h minus 1 plus theta k. Okay, that is the first one. Second one, again the mixed partial derivative they exist continuous, so value will be same. So, that means what will happen 2 times h k del 2f del x del y at the point 1 plus theta h comma minus 1 plus theta k, and plus k square del 2f del y square at the point 1 plus theta h comma minus 1 plus theta k. Okay. These 2 and these 2 get cancelled. You see these 2 and h square, see del 2f, what is del 2f? So, this is given, na. So, you just replace, so 2 and then 1 plus theta h, that means 1 by theta plus h whole cube, and then y to the power minus 1, that means minus 1 plus theta k, okay. Fine. So, that means in the denominator you will have 1 plus theta h to the power q and then times minus 1 plus theta k, and 2 will be there, there won't be 1 2 will be there, another 2 will be there, so that will get cancelled and you will end up with this one. What will happen in the last one, again k square del 2f del y square at the point 1 plus theta h minus 1 plus theta k, again 1 2 is there already in the del 2f, that this is the del 2f del y square, right. So, at the point x y, okay, of course. So, therefore, you just 2 get cancelled, I will just evaluate it 1 by x by 1 by y q, 1 by x means 1 by 1 plus theta h times minus 1 plus theta k to the power q, and this is the mixed partial derivatives, they are equal. So, therefore, 1 2 already will be there, 2 times h k. Okay. So, 2 again get cancelled, you will have h times k as it is, and divided by del 2 f del x del y, and it is there x square y square, that means 1 plus theta h square minus 1 plus theta h square. So, this kind of problem might be there if I want that, okay, you have a functions this and you have this point, you compute the first two terms of the Taylor's formula f near the point minus 1. So, this is formula is already given, you have to just perform the partial derivatives and you have to just conclude it. I think that is very kind of brief kind of about Taylor's theorem for several variable functions. So, if I have a scalar field, if I have functions from some set S, subset of R2 or Rn to R, then you will have explicit or you know the kind of you can have an expansion of your functions f near about that point, and that expansion you can approximate via polynomials of that variables. It depends from function where my function is defined. So, like in the single variable case, you can approximate f by a functions by a polynomial near about that point. Here also the similar sort of phenomenon is true in the context of scalar field. If I have a functions from Rn to R, then if Taylor's theorem you have the expansions of f near about the point an a1 to an. In other words, I can approximate my functions near about that point via polynomial of certain degree. It depends upon what order I am talking about the Taylor's theorem. So, I think that is all for the time being. So, I talked about mixed derivatives, I talked about Hessian, I talked about mean value theorem, then there is a extended mean value theorem, that means Taylor's theorem of order 1, and then you have a Taylor's theorem of certain order I have defined. It involves the partial derivatives of certain order. As an interpretation, I can approximate my functions with a polynomial. So, I think kind of real variable, single variable calculus little bit you can extend easily in this context. I think in my next lecture I will talk about related with that, and that will come in the next lecture. Thank you.